All right, let's just jump right into this. Welcome to this explainer where we're going to unpack one of the most famous and frankly most consequential debates in modern machine learning. If you work in AI or you're planning to, you've absolutely encountered the heavyweight title fight of the last decade, PyTorch versus TensorFlow. Today, we're cutting through all the noise and the Twitter hype to look directly at the design philosophies, the hard performance data, and the deployment realities that actually define these two titans.
And that really brings us to the million-dollar question we're tackling today. Which deep learning framework should you actually choose in 2026? Look, the landscape of machine learning is shifting at warp speed, but the foundation of almost every major breakthrough still relies on the software bridging our human ideas with intense computing hardware. Where you invest your time, and crucially, your team's resources today, dictates your ability to scale, deploy, and innovate tomorrow. So let's trace exactly how we got to this decision point. Starting with the rise of ML frameworks, how we evolved from writing custom code to relying on these modern titans. To really understand the stakes here, we have to go back to 2012. Back then, building a model meant painstakingly writing custom CUDA code just to get your program to talk to the GPU. It was brutal. But then, things changed. If you take standard, plain NumPy code running on a CPU and compare it to the PyTorch equivalent for a GPU, they are practically identical. PyTorch entered the scene feeling incredibly Pythonic. It replaced massive headache-inducing bottlenecks with immediate familiarity. You could basically swap out your NumPy arrays for PyTorch tensors, and boom, suddenly your computations were GPU accelerated. It was a literal game changer for the industry.
That brings us to the core philosophical divide: static versus dynamic execution.
You see, that early ease of use in PyTorch wasn't just about syntax. It represented a massive architectural divide. Early on, TensorFlow 1.x pioneered the static graph approach. You define your entire network architecture first, compile it, and then execute it in a session. This define then run model is fantastic for optimization, right? Because the framework sees the whole blueprint ahead of time and can allocate hardware resources perfectly. PyTorch, on the flip side, championed dynamic graphs, or eager execution. It's define by run. The graph is built on the fly, line by line, exactly as your Python code actually executes. And wow, did that architectural choice lead to a stark reality? It's perfectly summarized here. Graph mode is powerful for optimization, but deeply hostile to interactive debugging. Man, anyone who used early TensorFlow remembers this pain. If you had a bug deep in a massive neural network, you were just staring at this opaque, compiled block of math. You couldn't just print a variable halfway through to see what was happening. You were effectively locked out of your own code while it ran, making figuring out exactly where the math went wrong an absolute nightmare.
Which naturally leads us to PyTorch, the research king.
Because PyTorch evaluates operations immediately, line by line, researchers quickly realized they could just use standard Python debugging tools. A tensor holds a real value the exact moment you create it, meaning you could write data-dependent if statements totally naturally. This transparency crowned PyTorch the undisputed king of research. To put this into perspective, think of PyTorch as a highly flexible scripting language. It gives you the raw building blocks to do it yourself. TensorFlow, conversely, acts way more like a highly structured full application framework. It requires more boilerplate up front, but it comes with batteries-included abstractions that can massively speed up standard end-to-end data pipelines. Let's shift gears now to TensorFlow's home turf, production and deployment. While PyTorch was winning over the academic labs, TensorFlow was busy dominating industry and enterprise infrastructure. Because let's face it, when a model leaves the sandbox to actually serve millions of users, you need TensorFlow's deployment dominance. Since TensorFlow models started as these portable, compiled blueprints, Google was able to build a massive, mature ecosystem around it. Take TensorFlow Life, for example. It currently powers machine learning on literally billions of mobile and edge devices globally. That is wild. Then you have TensorFlow Serving for high-performance server infrastructure, TensorFlow JS for running models right in the browser, and of course, native, seamless integration with TPUs, Google's specialized hardware for massive scale. If you needed to ship a real product, TensorFlow had an out-of-the-box solution ready to go. Next up is the Great Convergence, or as I like to call it, stealing the best ideas. Okay, here is the plot twist of this explainer. In the world of open source software, a good idea doesn't stay exclusive for long. To stay competitive, both frameworks aggressively adopted their rivals' biggest advantages. TensorFlow realized their developer experience was a huge bottleneck, so with TensorFlow 2.x, they actually defaulted to eager execution. They made it act a lot more like PyTorch, integrating Keras to make building models incredibly user-friendly. Meanwhile, PyTorch realized they absolutely had to compete in production. So they introduced TorchScript, and more recently with PyTorch 2.0, dynamic Python bytecode transformation and graph compilation. PyTorch literally learned how to compile its dynamic code into optimized graphs to catch up in performance and deployment speed. They effectively met right in the middle.
So, how do you go about making your choice today?
Well, since the performance gap has significantly narrowed, your decision today is driven almost entirely by ecosystem advantages and your specific production needs. If you look at the landscape right now, if your work relies on cutting-edge pre-trained models, PyTorch is the clear, hands-down winner. It's the absolute default on platforms like Hugging Face, boasting over 50,000 models. However, if your ultimate goal is complex deployment, especially to mobile, edge devices, or browsers, or if you're relying heavily on Google's TPU hardware, TensorFlow and its newer sibling JAX offer native, first-class support that PyTorch still sometimes struggles to match smoothly.
Now, before we wrap up, we need to bust a few common myths. First off, please do not choose your framework based on Twitter hype. Base it on what your team actually knows how to use. Second, do not assume TensorFlow is dead just because academic papers mostly use PyTorch. That couldn't be further from the truth. TensorFlow powers a massive share of actual production systems globally. Third, just pick one framework and master it. The underlying math and concepts easily transfer. And finally, never start building a model without knowing exactly where and how you plan to deploy it.
Which leaves us with this final, somewhat provocative thought. As hardware gets more diverse and specialized, we're seeing the rise of tools like JAX, which focus heavily on compiler-driven optimization and higher-order gradients without all that traditional framework overhead. As ML compilers like XLA get smarter, bridging the gap between any Python code and the bare metal hardware beneath it, will this whole PyTorch versus TensorFlow debate eventually just become obsolete? It is a fascinating shift in the industry and absolutely something to keep your eye on. Thanks for joining me on this explainer, and keep learning.